Water in the water hose, the structure is something like this, squeezed down like this. And we like to say this is area A1, this is area A2, this is a V2, and here flowing is V1. According to the equation we have on the top, is A1 V1 equal to A2 V2. So V2 equal to A1 divided by A2 V1. So what does that say? So A2 is small. So V1 is small. So when this go through this, the V2, A1 divided by A2 is larger. So V2 is going to be larger than V1. So is that very obvious? Yes. If you care to water your lawn, you squeeze it. And what happens? The speed, the water is go faster. Equation. In this one, we still, this time, we like to using what we call conservation of energy to see what is going on. So in these cases, this one is A1, and here is delta X1, and this is a V1, and here press down is P1, and this going on here is P2, and here is A2, and then here is delta X2. Okay, so using reference point for potential energy. So the distance from here to here is Y2. The case from here to here is Y1. So in order for the column of water flow, this must have the work being done. So work done on the volume of water equal to what? When the work is being done, then very obviously we'll change what? Delta K plus delta U. So when the work done on a object, the kinetic energy changes and potential energy changes. So let's say the work done, the W times V, the boiler. So the boiler is here. Okay, so now we're looking at what is the change in kinetic energy. Delta K is equal to 1.5 m. The same mass, the same boiler, in which case V sub 2 squared minus 1.5 m V sub 1 squared. Okay, so now we like to investigate what is potential energy changes. Delta U is equal to mg Y2 minus mg Y1. So this is equation 2, equation 3, equation 4. You plug in onto this equation number 1. This is called conservation of energy, right? But what is the energy? So this is conservation of this equation number 1. So after you put all those down, then you have P1 minus equal to 1.5 m V1 squared, V2 squared minus 1.5 m V1 squared, and then plus mg. So now you divide the v on both sides, then m divided by v is equal to density. So this is become density, this become density, this become density, this become density. So immediately you will get something called P1 minus P2 is equal to 1.5 rho V2 square minus 1.5 rho V1 square plus rho GY2 minus rho GY1. By regrouping this, anything with the subscript number 1 put on one side of the equation, and anything with the subscript 2 in another equation, then you got the Bernoulli's equation. In which cases, Bernoulli equation stay at P1 plus 1.5 rho V1 square plus rho GY1 equal to P sub 2 plus 1.5 rho V2 square, and then plus rho GY2. So this is a Bernoulli equations. Okay, so the chapter 15 is done. Okay, now you have to use them. So for your study for the final, the example 15.7 is very unique, is a necessity. And then the other one is 31.33. 31.33 is good for your exam. And the other one is related with what we call the Boyle's force on the page 487, especially number 25. That is called the balloon experiment. We have a gentleman who is a balloon scientist working for 40 years at JPL, do this calculation over and over again. Balloon experiment. He designed a balloon. He said he need this first cut equation, and then after that he had to figure out finding what kind of balloon material and how to carry the load. And basically, the first 2 year physics is creating law career. That means you know that. So we are going to have a break.